We're going to be doing a game theory question, finding our pure strategy Nash equilibriums, and then we're going to be finding our mixed strategy equilibrium. All right, so when player 1 chooses top, player 2 is choosing right. When player 1 is choosing bottom, player 2 is choosing left. When player 2 is choosing left, player 1 is choosing bottom. When player 2 is choosing right, player 1 is choosing top. So we have two, as you can see, we've got two pure strategy Nash equilibriums. So two NEs at TR and BL. Okay, so that's all fine and dandy, but how would we make either player indifferent? Okay, let's say player 1 is playing top with a probability P and playing bottom with a probability 1 less P. And let's say player 2 plays left with probability Q and plays right with probability 1 less Q. So either player wants to find how to make either player indifferent. So for player 1 to make player 2 indifferent between L and R, player 1 needs to make, so we need to isolate for P now, and we need to find out what P is equal to. This is sort of important to note that these payoffs right here that I've written, this is 0, this is for left, and this is for right. This is L and this is R. This is playing top, this is playing bottom, this is playing top, this is playing bottom, and these are player 2's respective payoffs, okay? Right? Because when player 1 plays P, he's playing top, Q playing L. And it's player 1's job to make player 2 indifferent. So if you solve this, P should equal this. You should find that P equals 2/3, and I can prove this. So this is obviously 0 times anything. It's going to be that. So this is P4. Less 4, P6. Just some quick math. P equals 2/3, and we found that by putting either side equal to each other. Okay, so therefore, player 1 plays T, or top, with probability 2/3, and plays right with probability 1/3. Now we're going to do the same thing for player 2, because how is player 2 going to make player 1 indifferent? Okay, so very similar story, except in reverse. This is top has to equal bottom. This is when player 2 plays left. This is when player 2 plays right. This is when player 2 plays left. This is when player 2 plays right. And then the respective payoffs to what player 1 is getting. And you solve for Q. Just by looking at this, you can get an idea of what it might be. So player 2 plays left and right with 50% probability. And that's a straightforward indifference probability. So the notation for this, the mixed strategy equilibrium, how you'd write it out. Okay, so it's a little bit messy down there, But your mixed strategy Nash equilibrium, how you write it out properly, is bracket, bracket, 2 over 3, which is the probability of player 1 playing top, slash the probability of player 1 playing bottom, comma, bracket, the probability of player 2 playing left, and then finally, comma, the probability of player 2 playing right, bracket, bracket. So this tells the whole story of what each player is going to do. First with player 1 and their probability of playing top, going all the way through to player 2 playing right. And there you have it. You've solved for the mixed strategy Nash equilibrium, and you've written out the correct notation as well, or the correct way to the correct way to write down your answer. All right, that's it.